Welcome to part 2 of the Siglent SDG7102 review. Siglent has taken note of the issues I've shown in the review of this beta unit so far and is working them now. They've promised to send me an updated unit to review once they've fixed the issues. So let's talk about the IQ vector modulation. IQ, or in-phase or quadrature vector modulation, is a $3,000 option. The generator can vector modulate an RF carrier or output the IQ vectors directly. For direct vector output, set the carrier frequency to 0. I is on channel 1, Q is on channel 2. Channel 2 is disabled whenever the carrier frequency is not 0, and the modulated output is on channel 1. So now I have the function generator in IQ modulation mode. And when the carrier is set to 0 Hertz, you get the I and Q components on the output here. And right now I'm running those into the scope on an X and Y basis. So if we go here to data source, I can change what type of modulation we have. So let's go to 8-point phase shift keying. There we go. Let's go to 32, QAM, 16. There we go, 16. Sometimes it helps to stop and restart the scope. Binary phase shift keying, 2 points. Let's go to a 256-point QAM. And there it is. Now, one thing that's annoying about this is, let's say here I want to change the symbol rate, let's say to 20 kilohertz. Okay, nothing changed there. But now if I go and I change the data source, whenever I change this and come back, come on, there we go. It resets the symbol rate to 1 megasymbol per second, which I find annoying. I wish it would leave it alone. So let's go here. So yeah, there we are on the 8. That's what we have right now, 8. So I'm looking at the output of the IQ mode of this generator on my Tektronix 7904A 500 megahertz mainframe, but I'm using 200 megahertz plugins on X and Y. I have the X of the axis on I, the Y axis on Q, and the symbol rate is 1 million symbols per second, because that's the default symbol rate for this generator, and every time you switch modes, it switches symbol rate back to the default mode, which I find somewhat annoying, but that's what it does. But I'm doing this on the analog scope because some things just look better on analog oscilloscopes, and this is one of them. So let's look at the different IQ modes this generator puts out. Let's start with 2 ASK, 4 ASK, 8 ASK, BPSK, QPSK, 8 PSK, DB PSK, DQ PSK, D8 PSK, 8 QAM, 16 QAM, 32 QAM, 64 QAM, 128 QAM. That one does not look correct. 256 QAM, And this is 16 QAM_2. So I looked at these on the digital scope, and it just looks so much nicer on the analog scope. That's why I keep the analog scope around, because some things just look better. When we're in the IQ mode and you're outputting the signal on a carrier, only the positive output of channel 1 works. Channel 2 does not do anything. It only works at 0 hertz when you're putting out the modulation signal. So you can see here, we can turn that on and off. So now I'm running the modulated 8 PSK waveform into my spectrum analyzer, and I have it in modulation analysis mode. And so let's go back here. Symbol rate. So right now 1 megasymbol per second is the default. Now if I try and up the symbol rate on the spectrum analyzer, it will only go to 1.25. So now it's not matched, but I can come down here and go to 1.25 megasymbols per second, and it keeps up. Okay, but let's see let's go to spectrum analysis mode. And now here, watch what happens as I change the symbol rate to the spectrum. So as I lower the symbol rate, the peak goes up, and it gets narrower. So let's see if we can measure this, just for the hell of it. Measure occupied bandwidth. There we go. So here I can change the symbol rate, and it will measure the bandwidth that the symbol goes. So let's try a different waveform. Let's go here. Let's data source. Go to a 32 QAM, and then we'll go back. Okay. So yeah, so same thing. As I change the symbol rate, the bandwidth increases. So this IQ mode works fine, and it's I've never had a generator here at home that was able to do this, so I had tried this out on the spectrum analyzer, and this works pretty well. Okay, so for the spectrum analyzer measurements I've been making, and all of them except this one, I'm locking the spectrum analyzer to the clock in this in the SDG7102. This thing has a ovenized clock, and I have no reason to doubt that it's more accurate than anything else in my lab. I have nothing really to measure it with. I don't have a GPS reference or any other kind of standard frequency measurement. So I'm going to assume that they calibrated this correctly. So if you look here at the frequency error, you can see I'm getting a millihertz of average frequency error on a 500 megahertz carrier. So we disconnect but that's because the clock in this is matched to the clock in the spectrum analyzer. Now, you can see once I've disconnected the clock from this to this, you can see this waveform jumping around. Let's restart the measurement. And so at 500 megahertz, The clock in my spectrum analyzer is 266 hertz off from that in the waveform generator. Which one is right? Without a standard, can't say for sure, but I'm going to bet it's the waveform generator with its ovenized oscillator. Let's look at the pseudo-random noise spectra. The noise level was set to the maximum for the following spectra I measured, but I didn't take note of the setting. The noise voltage depends on the bandwidth of the instrument making the measurement. Just think of the 20 megahertz input limit on an oscilloscope, reducing the apparent noise. There were 4 types of spectrum measurements made. Average, which is the average value over as it sweeps through the frequency step. Sample is a sample as it sweeps through the frequency step. A positive peak is the largest value over the while it sweeps through the frequency step, and a negative peak, which is the smallest value over the frequency step. Each measurement was averaged 512 times, and the measurements were all made with my Siglent SVA1015X. I have the frequency scale set to the log mode, but the sweep itself is linear. So here, let's take a look at, we've got a 30 kilohertz bandwidth, but here this is only 16 averages, so you can see these are kind of messy. The yellow one in the middle is the one that's the average during each frequency step. The green is the sample during each frequency step. The blue is the highest value, and the purple is the lowest value. Now we've gone to 512 averages, and you can see things have smoothed out quite a bit. So at 30 kilohertz, we're getting minus 33.2 dBm out of the unit. We can see that there's about a 1.5 dB rise at 270 megahertz, and the 3 dB bandwidth is 370 megahertz. And the peaks are 9 dB above, and the values are 15 dB below the average level. Now we go to 100 kilohertz, and because the bandwidth is wider, we've come up in level, so now the level's minus 27.5 dBm, and these differences have shrunk a bit. We still have the 370 megahertz 3 dB bandwidth. Now at 300 kilohertz, we've come up some more to minus 22.7 dBm, and again, these have shrunk some more. And now here we're at 100 megahertz, well, 1 megahertz bandwidth, not 100. And we're up to minus 17.6 dBm output level. Again, the level's higher because my bandwidth is higher. And you'll notice on all of these, this noise spectrum is absolutely flat out to 100 megahertz. We have about the 1.5 dB peak, and it keeps the 370 megahertz 3 dB bandwidth. So I think this is pretty good for a random noise spectrum out of a function generator. I give it a thumbs up. And if you like this video, please consider giving this a thumbs up as well and subscribe. Let's talk about the pseudo-random binary sequence that this function generator does. Pseudo-random binary sequences are used to characterize the effect of noise and distortion on binary data communication links using an eye diagram. This function generator will generate single-ended and differential PRBS waveforms up to 312.5 megabits per second. And it will do PRBS 3, which is a 7-bit, to PRBS 32, which is over 4 billion bits long random sequences, where the sequence is 2 to the n minus 1 in length. The second channel frequency is linked to the first channel PRBS bit rate, and the channel 2 frequency will be half of that bit rate. I discovered this after I made some of the clips, mostly because I don't like to RTFM. And this makes a perfect sync signal for the eye diagram. The oscilloscope should always use a waveform locked to the source and never triggered on the PRBS data stream. That's the only way to measure jitter and dispersion. And for the PRBS examples here, channel 3 of the scope is being triggered by channel 2 of the function generator, as seen in this diagram up here. So let's go from square wave mode into pseudo-random bit sequence mode. And we have various lengths of bit sequences we can do. Let's try doing this. So this is really... Oh, this is getting very long. 2 to the 32nd. 20, and let's see how fast we can go here. (312.5 megasamples per second). Let's go back to, let's say, 10 megabits per second, just so we can see this on the scope here. So we can get this is very long. Now let's look at the logic levels we've got. TTL CMOS, low voltage TTL and CMOS, emitter coupled logic, low voltage positive emitter coupled logic, low voltage differential signals in custom. Right now we're in custom. Let's see what levels we get with TTL and CMOS. Okay, it's shifted it all positive. So let's look and see where we're at here. Vertical menu, position. Let's go -3. Okay, so there's the levels for low voltage TTL and CMOS. Let's try low voltage TTL. It drops it down. Low voltage differential signal. Can we go to okay, so that's above ground. VDDS. Echo. That's below ground, so let's go here. Go to 3. Okay. Low voltage positive echo. Okay, so now I've switched the ground level down to there. So these are kind of useful built-in levels. Now let's, I'm just curious, we can go to differential on this. I've done it. So to go to differential mode, go here, output setting, channel 1 output, format, differential. Okay, so now both outputs are on. So if you look at this chart on the front of the signal generator, you can see I have channel 1 coming out the channel 1 output, and I have channel 2 coming out as the sum of channel 1 and channel 2. Now, if you look at channel 1, let's look here at channel 1, we can see I have a 2 to the 32-bit length pseudo-random bit sequence, and 1 volt peak to peak, which is the maximum I can do, differential, 310 megahertz. And I have to use a multiple of 10 megahertz for this particular test because I'm syncing off the 10 megahertz clock of the signal generator. Now, in channel 2, which is being summed in, I have noise. And so now if we look down at the scope, you can see I have here are the eye diagrams for channel 1 and channel 2. Now let's see what happens when I up the noise coming out of channel 2. You can see now that I get the noise summed into the pseudo-random sequence, and you can see that the eye diagram coming out of the mixed noise and pseudo-random sequence is closed vertically. This is just an example of the summing you can do with this and the pseudo-random sequence. So here I have another pseudo-random bit sequence eye diagram example. So channel 1, I'm putting out the pseudo-random bit sequence at 1 volt peak to peak and 312.5 megabits per second, which is the highest data rate this will put out. On channel 2, I have a square wave at 312.5 megahertz, and I'm syncing off the square wave. And then I'm varying the delay on the square wave. Here you can see, as I vary the delay here, you can see I shift the eye diagram. So I've got the delay set up to center my eye diagram on the scope. So let's go back to channel 1. Now watch so right now I have the rise and fall time set at 500 picoseconds. And I believe it is 500 picoseconds. It's close enough to the 400 picosecond rise and fall time of this oscilloscope that I can't really get an accurate measurement. And so the overshoot we see here in the eye diagram may actually be a bit bigger. But watch what happens now to the eye diagram as I increase the rise and fall time. The overshoot goes away. There's the bad spot. Okay, yeah, so there it's shifting over. So now if I want to center that, I can come back over here and do there. There, I've centered the eye diagram now. So this is now with the rise and fall time at 1.3 nanoseconds. And we can go back to 0.5 nanoseconds. And then then to center the eye diagram, I come back over here and I can adjust this and center it. So this is just another example of the pseudo-random bit sequence that this signal generator is capable. So here I am testing a 20 hertz to 120 megahertz RF amplifier. 15 volts is coming from this HP 5216A power supply, and the voltage is being monitored by this Keithley meter. The output of this waveform generator is going into a resistive power divider. One half of that power divider is going to the input of the amplifier, and the other half is going into channel 2 of the oscilloscope, which is the blue trace. The output of the amplifier is going in through a 20 dB attenuator into channel 3, that is the yellow trace. Okay, so now we've zoomed in on the screens. So we can see that I have this in pulse mode, and I've got it set for a 5 megahertz signal, 45 millivolts peak to peak, 50% duty cycle, with a falling edge of 8 nanoseconds and a rising edge of 8 nanoseconds. Now, 8 nanoseconds is the fastest rise and fall time I can do with the function generator I own. But let's see what happens to this waveform as I vary the falling edge. Drop it to 7. 5 nanoseconds, you can see that there's some ripple now in the top and a little bit of ripple on the input. So that's probably the fact that as this amplifier goes nonlinear, it's reflecting some of the signal back, and it's not clear whether the ripple in the output is due to the reflections on the input or other stuff going on. But let's 4 nanoseconds. 3 nanoseconds, 2 nanoseconds, 1 nanosecond, 500 picoseconds. So I would never see this with the function generator, but you can see that there's some nasty ringing in the output of this amplifier because it just does not like the fast rise and fall time. So let's change this back to the 8 nanoseconds it's happy with. 2, 3, 4. And there we are back with the 8 nanosecond rise and fall time. Okay, so now I'm testing the same amplifier, but the input signal is now a pseudo random bit sequence at 40 megahertz, same amplitude, and the scope is being triggered off a synchronized 20 megahertz signal from channel 2. So let's go back to channel 1. So what I'm looking at are eye diagrams. Now the top is the eye diagram for the input, the bottom is the eye diagram for the output. Let's see what happens now is I lower the rise and fall time. With the pseudo-random bit sequence, they're linked, which is nice. So here's 5. You can see the ripples starting to develop in the output. Now you can see it on the input at 4, 3, 2, 1, 0.5. Anyway, so this demonstrates the usefulness of both the pseudo-random bit sequence and the variable rise and fall time of this function generator. A very nice feature. We've reached the end of part 2 of this review. If you like this review, please give it a thumbs up. And if you want to make sure you see the next review, please subscribe. Thank you for watching.